Yeah, another type of ionization is atmospheric pressure chemical ionization. As name indicates, it operates under the atmospheric pressure. Okay? Let's look at this figure. Um, Here, heat and coaxial flow of nitrogen. Here, this one nitrogen converts eluate into a fine mist from which solvent and analyte evaporate. You see, here this is from the your sample from liquid chromatograph now enters this this needle. Then here you also you flow the nitrogen gas, dry nitrogen gas. This is a nebulizing gas. So at the tip of this needle nebulizer, there is a fine mist. Okay, and here you this part is high. The temperature is maintained at very high temperature. 500 degrees C, and this is like other ionization technique, but difference is that here you need this needle, right after this part, and then you apply very high potential, 6,000 volt, right? It creates corona discharge, and here your samples are ionized. Okay, there are cations and anions, and now it enters this quadrupole mass spectrometer. But here this is skimmer. This is between the skimmer and this plate. You apply this potential. Since this skimmer potential is more negative, so only the positive ions are pass through this hole and enters the quadrupole mass separator. Okay. The distinguishing feature of this technique is that high voltage, as I said, high voltage is applied to a metal needle in the path of aerosol. And this is aerosol using this nebulizing gas, nitrogen gas. This sample is becomes fine aerosol, right? And then this aerosol here, by using this metal needle, becomes ionized. Okay. An electric corona. Corona is a plasma containing charged particles forms around the needle here, ejecting electrons into the aerosol and creating ions. Okay. Here electrons are now collide with your samples, and it creates ions. Okay. Here is an example. Let's see how this molecule and this proton, this ion is formed. Okay, since you used nitrogen gas, then it is collide with the electrons, and then it becomes N2 cation radical, right? And this cation radical reacts with another neutral nitrogen gas, and then it creates this rather very peculiar ion, N4 cation radical ion, and it collide with the water molecule, and then water molecule becomes the cation radical, and this radical also reacts with the water molecule and becomes the hydroxyl radical, right? And also this hydrogen ion, and hydrogen ion now reacts with NH2O, so it becomes this aggregates. Okay, and now this aggregate reacts with a molecule, right? And then it creates this MH plus, this ion. Okay, and this ion is enters the mass spectrometer. Analyte M might also form a negative ion by electron capture. Okay? By directly capturing electrons, right? It becomes a negative ion. Okay? And if molecular structure is like that, X and Y, in the eluate might create a negative ion by the reaction, right? This one now collide with the electrons, and then this bond is broken, and it creates a negative ion part, right? Y minus. The species Y minus could abstract proton from weakly acidic analytes AH, yeah? And this anion may collide with AH, and then it abstracts the proton, so creating this A minus anion. Atmospheric pressure chemical ionization tends to produce single charge ions and is unsuitable for macromolecules such as proteins. Okay? And usually, as you see, charge is just a single. All the ions are singly charged ions. Okay, so it is unsuitable for macromolecules such as proteins, because proteins molecular mass is really high. Okay, and when these molecular ions are singly charged, so mass to charge ratio becomes very high. Yeah, so it is not suitable for for the measuring the molecular mass of proteins, right? As you'll see, soon, for protein detection, the protein molecular ion should be multiply charged, not singly charged. For example, not +1 but +n. Okay, you'll see soon. It will be very interesting. Okay, next topic is selected ion monitoring and extracted ion monitoring. Yeah? Okay, this figure A is the chromatogram, yeah, from from LC, yeah, using UV, violet, ultraviolet detection. Okay, here you see there are many peaks here, maybe 1, 2, 3. There are at least 6 peaks, okay, with a very large background. Okay, this is broad hump. There are many natural substances in the river water, right? So this is not an ideal case because this background is very broad. Okay? Actually, this chromatogram was obtained from the river. The river water sample is spiked, okay, and using a ultraviolet detection. Okay, usually the detector for LC is UV detector. Okay, that it works very nicely, but in this case it's not very good. So if you use mass spectrometer as a detector, okay, and instead of using this UV detector, you use mass spectrometer as a detector for LC, and then you do the same thing in terms of as a function of time. You detect not absorbance but total ion current. Okay, and then you get a much nicer peak. Yeah, this is this kind of spectrum is nicer than this spectrum. Yeah, this is background is well removed. Okay, this is a reconstructed total ion chromatogram. Okay, and but let's see, you want to monitor a specific chemical. Yeah. For example, this one, yeah? imazaquine, yeah? From this UV chromatogram, or this ion chromatogram, although you obtained these peaks, but you don't know which one is which, right? But you now suspect the sample contains this molecule, this very complicated molecule called imajaquine, and then you want to monitor this one, and since you know the structure and then you know the molecular weight, and then assuming that this molecule contains the proton, right? Proton, and then this mass to charge ratio is 312. Okay, how do you detect this one? And then you operate mass spectrometer. You set detector at this this mass, okay, and then you do the you operate the LC, and then in this case you only monitor the mass to charge ratio 312, not all these peaks, because you already set your mass spectrometer at this mass to charge ratio, and then you obtained only one peak here, right? At this time, maybe time 20 around 6, you see, and then compare with this one, this ion chromatogram, right? Total ion chromatogram, because it detects all the signals, right? And then you now know that this peak 6 is due to this imajaquine, the molecule of your interest. Okay, this way you can now you can simply say that this reverse sample contains this one, this herbicide, all right, and this peak is it. And okay, and then what's the total? The extracted ion chromatogram, right? And then this is also total ion chromatogram, right? So like this one, then you use your mass spectrometer as a LC detector, okay? And the sample here in this case is the fruit-based soft drinks from London Gatwick Airport, okay? And then there are many peaks here, right? A lot of peaks here. This is total ion chromatogram, right? And you want to know the each peak, There are many peaks, but you want to know what is this each peak, right? And in this case, you scan entire the spectrum, okay, and then for example, if you want to detect this molecule, this is bendazole, right? And then you know the mass to charge ratio, and then you set your mass spectrometer at this mass, and then run, okay, and then you get this one, and then also at the same time you obtained this mass spectrum, okay. That way you can extract ions, individual ions, and then you get the this mass spectrum also, okay. So first get total ion chromatogram here, and then set the mass to charge ratio at a specific value, in this case at 200, 2.043, and run MS and find time for that peak, okay. You run this mass spectrometer, so you get both, right? This one and this one.